In this lecture video, we look at inference procedures for comparing two population means using independent samples where the population variances are unknown but can reasonably be assumed to be equal. Now here's a sampling framework. We have two samples, one from each of the two populations under consideration. We're going to let y denote the random variables for the observations in the two samples, and to distinguish between the two samples as well as the observations within a sample, we're going to use double subscripting. So the first subscript will indicate the sample, and the second subscript will indicate the observation within the sample. So for example, y11 is the first observation in the first sample, y21 is the second observation in the first sample, and so forth out to y sub 1 comma n1, which is the last observation in the first sample. This is a random sample of size n1 from a population with mean mu1 and variance sigma squared. The second sample, the values are y21. This is the first observation in the second sample, y22, the second observation in the second sample, and so forth out to y sub 2 comma n2. This is the last observation in the second sample. This is a random sample of size n2 from a population with mean mu2 and variance sigma squared. Now, the two samples are assumed to be drawn independently of one another. And notice that, again, the two sample sizes do not need to be the same, right? They can be different. That's very good from the standpoint of study design and so forth. So the sample sizes can be different. But I do want to point out to you that the population variances are not subscripted with the population number. And this is because, again, we are assuming that the population variances are the same. And so we're going to denote the common value by sigma squared without any kind of a subscript. Now let's come up with the notation or define the notation for the summary statistics for the two samples. So y bar 1 will be the sample mean, the mean of sample 1. S1 squared is the variance of sample 1, and S1 is the standard deviation of sample 1. Similarly, y bar 2 is the mean of sample 2. S2 squared is the variance of sample 2, and S2 is the standard deviation of sample 2. Now, if the population variances are in fact equal, again, we're denoting their common value by sigma squared, then note that S1 squared, the variance of sample 1, and S2 squared, the variance of sample 2, are both unbiased estimators of sigma squared. You'll recall from our discussions in the context of sampling distributions, and in particular when we were talking about the sampling distribution of the sample variance, we showed that the mean of the sampling distribution of the sample variance is always equal to the variance of the population from which that sample is obtained. So S1 squared is an unbiased estimator of the variance of population 1, and S2 squared is an unbiased estimator of the variance of population 2. But if the two population variances are equal, say sigma squared, then S1 squared and S2 squared are estimating the same quantity. Now, because they're estimating the same quantity, we can pool that information together to come up with an estimator of sigma squared that is better than either of S1 squared or S2 squared individually. Now, the way that we do this is we calculate a weighted average of the two sample variances, and we're going to call that weighted average a pooled estimator or a pooled sample variance. So the pooled sample variance is an estimator of the common population variance, and in fact it is also an unbiased estimator of that common population variance. Now you'll note here that both S1 squared and S2 squared are in the numerator of this pooled sample variance. And you'll note that this is in fact a weighted average. You'll remember that a weighted average is a weighted sum divided by the sum of the weights. And so you see here that the weight associated with S1 squared is the number of degrees of freedom associated with sample 1. The weight associated with S2 squared is the number of degrees of freedom associated with sample 2. And also, you'll note that if we add those two numbers of degrees of freedom together, n1 minus 1 plus n2 minus 1, we get n1 plus n2 minus 2, and that's what's in the denominator. So the pooled sample variance is, in fact, a weighted average of the two sample variances. And again, because each of these sample variances is an unbiased estimator of sigma squared, and because we're taking a linear combination of those two sample variances, the pooled sample variance is also an unbiased estimator of the common population variance. Now, we can use that along with the mean of the sampling distribution of the difference in the sample means. We can calculate the studentized version of the difference in the sample means. So y bar 1 minus y bar 2 is an unbiased estimate. Well, let me put it this way. The mean of the sampling distribution of y bar 1 minus y bar 2 is mu 1 minus mu 2. What I was going to say first is that, and this is correct as well, that y bar 1 minus y bar 2 is an unbiased estimator of mu 1 minus mu 2. So we've got this statistic, y bar 1 minus y bar 2, and we're subtracting from it the mean of its sampling distribution, mu 1 minus mu 2, and then we're dividing that difference by the estimated standard error of the difference in sample means y bar 1 minus y bar 2. Now, based on an argument that is completely analogous to the argument that we used in the previous module when talking about the t-distribution and talking about why the studentized version of the sample mean in that context has a t-distribution, the same argument or the same type of argument applies here. And so this studentized version of the difference between the sample means has a t-distribution with degrees of freedom equal to n1 plus n2 minus 2. So for the to perform hypothesis tests about that allow us to compare the population means where we don't know the population variance, but it is reasonable to assume that the population variances are equal. Okay, this is the formula for our test statistic, t-calc. We have in the numerator of t-calc the difference in the sample means. From that, we subtract the hypothesized value of mu 1 minus mu 2, and then we divide that difference by the estimated standard error of y bar 1 minus y bar 2. And again, I've replicated the formula for the pooled sample variance here, just so that you would have it on one page, one slide. The sampling distribution of t-calc, if the null hypothesis is true, then and also as long as if the two populations are normally distributed, then the t-calc will have students' t-distribution with n1 plus n2 minus 2 degrees of freedom. If the populations are not normally distributed, then under the assumption of the null hypothesis, t-calc will be approximately distributed according to students' t-distribution with n1 plus n2 minus 2 degrees of freedom. So we have our three hypothesis tests as we have in the past for comparing, in this case, the two population means. We have our two-tailed test, test A. We have our left-tailed test, test B. And we have the right-tailed test, test C. Now, the rejection criteria for each of these three kinds of tests is very similar to what it was for the z-test in the previous lecture, and the only difference here is that we are getting our critical points from a different reference distribution, in particular the t-distribution with n1 plus n2 minus 2 degrees of freedom. And so you see the critical points for these three tests. Now, the formulas for the p-value for the three tests are given here, and these should look very, very familiar to you. These are the same formulas that we had for the one sample t-test back in the previous module. The only difference here is in the number of degrees of freedom associated with the t random variable. Now I see that I have a typo here. These inequalities should be non-strict. And so I'm going to fix those right here. And so voila, I fixed that typo. Make sure you fix those typos in your note packet if they are there. And so for the two-tailed test, the p-value for the test is equal to 2 times the probability that a t-random variable with n1 plus n2 minus 2 degrees of freedom is greater than or equal to the absolute value of the observed value of our test statistic. If we're performing a left-tailed test, then the p-value is equal to the probability that a t-random variable with the appropriate degrees of freedom is less than or equal to the observed value of the test statistic. And if we're performing a right-tailed test, then the p-value is the probability that a t-random variable with the appropriate degrees of freedom is greater than or equal to t-calc. Now, recall from the previous module that when we are using a t-table or a set of t-tables, we're not going to be able to determine the p-value exactly. In most cases, the best we'll be able to do is to approximate it using an interval based on the information that is obtained or that's provided in the t-table. So we just need to keep that in mind. On the other hand, if you're using computer software like SAS or Minitab or SPSS, then the p-value will be calculated for you. In addition, if you have a calculator such as a TI-84 or a TI-36X Pro, at least I know the 84 has the t-distribution built in, and I think that the 36X Pro does as well. But anyway, so some calculators will be able to calculate the t-value for you, but for the purposes of this class, at least on exams and things like that, I'm going to have you use the tables. Okay, so let's also look at how to construct confidence limits for estimating the difference between mu1 minus mu2. And so since the random variable, and this is the studentized version, again, studentized version of the random variable of the difference in the sample means, that has a t-distribution with n1 plus n2 minus 2 degrees of freedom. And so it follows that the probability that that random variable is less than or equal to the upper alpha percentage point of a t-distribution with n1 plus n2 minus 2 degrees of freedom, that probability is 1 minus alpha. And we can rearrange the event, the terms defining the event inside the parentheses in order to get mu1 minus mu2 on one side of the inequality all by itself. And so this shows us that the probability that y bar 1 minus y bar 2 minus the t-value, the interval coefficient, times the estimated standard error of y bar 1 minus y bar 2, the probability that that random variable is less than or equal to the difference in the population means, mu1 minus mu2, that probability is 1 minus alpha. And so that implies then, in repeated sampling, that the random variable, okay, given here, will be less than or equal to the difference in population means mu1 minus mu2, approximately 1 minus alpha times 100% of the time. Equivalently, we can state that in terms of mu1 minus mu2. So the difference in population means mu1 minus mu2 will be greater than or equal to that random variable approximately 1 minus alpha times 100% of the time. Now, for this reason, that random variable, y bar 1 minus y bar 2 minus the t-value times the estimated standard error of the difference in sample means, that is called a 1 minus alpha times 100% lower confidence limit for mu1 minus mu2. Again, the way that we interpret this, once we have it, once we've got our data, the two samples, and we've calculated everything, and we've calculated this lower confidence limit, we say that we are 1 minus alpha times 100% confident that mu1 minus mu2 is greater than or equal to this lower confidence limit. All right, similarly, the probability that the studentized version of the difference in sample means is greater than or equal to the negative of the upper alpha percentage point of this t-distribution is 1 minus alpha. And so that implies that the probability that the difference in sample means plus the t-value times the estimated standard error of the difference in sample means is greater than or equal to mu1 minus mu2 is also equal to 1 minus alpha. And so because of that, the random variable, what that implies is that the random variable given here will be greater than or equal to the difference in population means mu1 minus mu2 approximately 1 minus alpha times 100% of the time. Equivalently stated, we can say that the difference in population means mu1 minus mu2 will be less than or equal to the random variable given here approximately 1 minus alpha times 100% of the time. And so for that reason, the random variable given by the difference in the sample means plus the t-value times the estimated standard error of the difference in sample means is a 1 minus alpha times 100% upper confidence limit for the difference in population means mu1 minus mu2. Once calculated, we say that we are 1 minus alpha times 100% confident that mu1 minus mu2 is less than or equal to this lower confidence limit. Now, whoops, I called it a lower confidence limit here. It's actually an upper confidence limit, so I need to change that, don't I? Okay, so there I fixed that. Okay, now if we compute both a 1 minus alpha over 2 times 100% lower confidence limit and a 1 minus alpha over 2 times 100% upper confidence limit, then we put them together, then we have the endpoints of a 1 minus alpha times 100% two-sided confidence interval estimate of mu1 minus mu2. And once we've computed the endpoints and constructed this interval, we say that we are 1 minus alpha times 100% confident that mu1 minus mu2 is somewhere in this interval. So let's look at an example. So mesquite is a thorny bush whose presence reduces the quality of pastures in the southwest United States. In a study of growth patterns of this plant, dimensions of samples of mesquite were taken in two similar areas, labeled A and M, of a ranch. We are interested in determining whether the average heights of the plants are the same in both areas. Now, we saw this example before, and we looked at this in the context, or in the section, where we were comparing two population variances. All right? And we said at that time that we were looking at that example there because the way that we compare the population means depends upon whether it's reasonable to assume that the population variances are equal. Now, you'll remember that we failed to reject the null hypothesis in that example. We failed to reject the null hypothesis that the population variances are equal. And so then it's reasonable to assume that the population variances are equal. And so while we haven't proven that they're equal, we never prove the null hypothesis, do we? We always are trying to reject the null hypothesis. And if we can't reject it, we just say we fail to reject. But what we can do is proceed as under the assumption that the null hypothesis is true. That's what we're going to do here. Is it reasonable to assume that the population variances are equal? Yes, because we failed to reject the null hypothesis that they are equal. So data for the two samples are found in, we don't have the raw data. We do have the sample data here for both samples. And we're going to use this to perform the appropriate test in this situation. And we're going to use a 0.01 level of significance. Now, in addition, as a follow-up to that test, we're going to construct a 99% confidence interval estimate for the difference mu 1 minus mu 2. I've got, I'm going to, in the previous lecture or in the previous section, we used mu 1 minus mu 2, and so I want to be consistent with that, so I'm going to modify this a little bit to get consistent with that. Okay, so I've modified my notation so that my subscripts are 1 and 2 rather than A and M. So make sure, if your notes use A and M, make sure that you change those to 1 and 2 as I've done here. Okay, so let's let mu1 denote the average height of mesquite trees in area A, mu2 the average height of mesquite trees in area M, and so the hypotheses to be tested are given below. The null hypothesis is that the difference between the population means mu1 minus mu2 is equal to 0 against the alternative that the difference is not equal to 0. Now that's equivalent to testing the null hypothesis that the two population means are equal against the alternative that the population means are different. And again, we're to use a significance level of 0.01 in performing this test. Now the formula for the test statistic, t-calc, is the difference in the sample means y bar 1 minus y bar 2 minus the hypothesized difference, 0, divided by the estimated standard error of the difference in the sample means. All right, and let's see here. So we, the number of degrees of freedom, notice that we have 20 observations in sample 1 and 26 observations in sample 2. And so n1 plus n2 is 46, minus 2 is 44. So this test has 44 degrees of freedom associated with it. And we're performing the test at the 0.01 level of significance, and it's a two-tailed test. So we need to divide that alpha, that significance level, by 2, 0.005, and we're going to put 0.005 probability in either tail. So the critical points for the test are, the lower critical point is negative 2.692, and the upper critical point is positive 2.692. So we're going to reject the null hypothesis if t-calc is either less than negative 2.692 or if it's greater than positive 2.692. Now the pooled estimate, in order to calculate the t-statistic, we need to calculate the pooled estimate of the population variance. And so we're going to take the standard deviations, square them to get the sample variances, multiply them by the appropriate degrees of freedom, and then divide by the sum of the degrees of freedom, which is 44. And so SP squared is 0.1947. Now that is between the two sample variances. If you square 0.5155 and 0.3751, you will get sample variances that bracket the 0.1947. And so the pooled sample variance is somewhere between the two sample variances, which it must be the case that that happens because, again, the pooled sample variance is a weighted average of the two individual sample variances. So we then plug that 0.1947 into the denominator, the formula, right here, all right, along with the other sample values, and we get a test statistic t-calc of 2.78. So since 2.78 is greater than 2.692, we reject the null hypothesis and conclude that the difference in the population means mu1 minus mu2 is not equal to 0. In other words, we are concluding that the two population means are different. And so we can conclude that there is sufficient evidence at the 0.01 level of significance to conclude that the mean heights of the mesquite trees in the two areas are in fact different. Now, let's look at using the p-value method. And so remember that because this is a two-tailed test, the p-value is going to be equal to 2 times the probability that a t-random variable with, in this case, 44 degrees of freedom is greater than or equal to 2.78. Now, from the t-table, we can tell that the probability that a t-random variable with 44 degrees of freedom is greater than or equal to 2.78, that probability is between 0.001 and 0.005. Now, the p-value is twice that probability, so if we multiply everything in this string of inequalities by 2, we get the result that the p-value must be greater than 0.002 and strictly less than 0.01. Now, we're using a 0.01 level of significance. The p-value is, we know it to be less than, strictly less than 0.01, so it is less than or equal to 0.01. And so, therefore, the rejection criteria stated in terms of the p-value method has been satisfied. And so, using a p-value method, we see that we would reject the null hypothesis at the 0.01 level of significance. Okay, and we also want to construct a 99% confidence interval estimate of mu1 minus mu2. And so again, here is the formula that we saw for that. And I'm sorry, no, not a lower confidence limit, but a two-sided confidence interval. I think I misspoke. We performed a two-sided test, and so we want to construct a two-sided, 99% two-sided confidence interval. And so this needs to be minus plus. Let me go fix it real quick. Okay, so that's been fixed right there. And so we end up getting a two-sided confidence interval of 0.0112 for the lower endpoint and 0.7178 for the upper endpoint. And so we can say that we are 99% confident that the difference in the population means is somewhere between 0.0112 and 0.7178. Now notice that 0 is not in this interval. 0 is strictly to the left of that lower endpoint. And so based on that, because 0 is not included in this interval, it's not one of the plausible values for the difference, mu1 minus mu2, at least at the 99% confidence level. So we can conclude then, we know that based on that, we can conclude that mu1 minus mu2 is not equal to 0, and in particular, we could conclude that it's greater than 0. Now, if we add mu sub 2 to everything in this string of inequalities, we clear that difference in the middle, and we can conclude at 99% confidence that mu1, the mean height of the mesquite trees in area A, is somewhere between 0.0122 and 0.7178 units higher than the mean height of trees the mean height of the mesquite trees in area M. Okay, so that wraps up the examples that I wanted to show you on how to compare two population means using one sample, using samples from each of the two independent samples from each of the two populations, where the population variances are unknown, but it's reasonable to assume that they are equal.